Intro to fractions. I realize that fractions are not necessarily everyone's favorite topic. I hope to convince you during the course of the rest of this module that you can actually do fractions. You can make sense of this topic. Let's start at the beginning. Here's a number line with a few fractions. Of course, most of the fractions fall between the integers. Notice that fractions can be positive or negative. Also, there are an infinite number of fractions between any two integers. So between, say, 1 and 2, there's an infinity of fractions. We won't spend a lot of time on this idea, but it's just an important perspective to have on some of the things the test will ask about fractions. Notice that any negative fraction can be written with the negative sign in a few different places. For example, we could have the negative sign out in front of the fraction, negative 1/5. We could also write the negative in front of the 1, so negative 1 divided by 5. We could also write 1 divided by negative 5. So all three of those are perfectly equivalent and interchangeable. And we could switch back and forth freely between them. Sometimes people get really locked up. They think that that negative sign has to sit in one place and can't move. Well, no. All three of these are equivalent. You're free to move that negative sign around. So the test will actually expect you to have that fluency. So let's talk about some terms. Suppose we have the fraction 3 over 16. What do we call the place where the 3 is sitting and where the 16 is sitting? The top part, the upstairs of a fraction, is the numerator. This fraction has a numerator of 3. The bottom part, the downstairs of the fraction, is the denominator. This fraction has a denominator of 16. Two ways of thinking about a fraction. Well, first of all, we can think of it as division. 2/7 means 2 is divided by 7, so there's an actual arithmetic operation occurring. A completely different way is pieces of pie. If a pie, a hypothetical pie, is cut into 7 equal pieces, then 2/7 means 2 of those 7 pieces. It would mean this much of the circle. So notice that the first one, you could call it an arithmetic way of thinking about fractions. The second one is more of visualization. And it's actually very important to cultivate both of these because these employ different sides of your brain. And if every time you look at a fraction you think both of the division as well as the diagram, then you're going to be using both sides of your brain and you're going to be understanding fractions much more deeply. For a fraction such as 35 over 5, it's useful to think about the fraction as division because that division we can actually perform. 35 divided by 5 equals 7. Notice that 35 over 5, that in every way is an equivalent way to write the number 7. When we write 35 over 5, we are writing the number 7 in kind of a hidden form. This leads to the idea of equivalent fractions. Two fractions are equivalent if they have the same numerical value, even though they have different numerators and different denominators. So 2/3 equals 10/15. Those fractions are equal. We are totally allowed to put an equal sign between them, which of course is a very powerful statement. We're saying that those two have exactly the same mathematical value, even though they look very different. And in fact, one way to see what's going on here, we can write the 10 and the 15 as products. 2 times 5 over 3 times 5. In other words, the numerator and the denominator of the original fraction both got multiplied by the same factor. And in fact, we can expand that idea. If we are given one fraction, we can always find an equivalent fraction by multiplying the numerator and the denominator by the same factor. So for example, we start out with 3/8. We could multiply the numerator and the denominator by 4. This would give us 12 over 32, an equivalent fraction. Essentially, we are multiplying the fraction by 4 over 4, which equals 1. As we can multiply both numerator and denominator by the same factor, we can also factor out the same positive integer from both the numerator and the denominator. So for example, suppose we have 6 over 42. Well, we could express both of those as products. 6 times 1 over 6 times 7, and then we can factor out those 6 and cancel them. and get down to 1/7. The 6's cancel. Notice that canceling is a form of division. That's very important. Canceling is a form of division. Some folks have misconceptions about canceling. And canceling the common number in the numerator denominator does not merely, quote, go away. A lot of people have this sloppy way of talking about it. The 6's go away. That's not a very healthy way to think about this. It leads to mistakes. For example, suppose we had 8 over 40. We wanted to simplify it. Well, clearly, we can cancel the 8's. So 40 divided by 8 is 5. That gives us the denominator. Well, people who are stuck on the concept of 8's go away, well, then they wonder what happens in the numerator. What if the 8 goes away? What's left in that numerator? Instead of thinking of it in terms of the 8's go away, we cancel the 8's. That is to say, we divide by the 8's. And 8 divided by 8 is 1. The 8's don't go away. They divide 8 over 8 to equal 1. This is a crucially important idea for anyone who previously has been using the go away understanding of canceling. The equivalent fraction with the lowest possible integer value of numerator denominator is the fraction written in lowest terms. So for example, we start out with 72 over 96. Both of those are divisible by 6. We can divide down to 12 over 16. Both of those are divisible by 4. We can divide down to 3 over 4. We cannot divide any further. That fraction is in lowest terms. Once the fraction is in lowest terms, we cannot simplify any further. Lowest terms is also known as simplest form. Make a habit of always, always, always writing all your fractions in simplest form. Well, why? First of all, it will make all your calculations much easier because you'll be dealing with smaller numbers. On the GRE multiple choice, the answer choice listed will almost always be in simplest form. So you'll have to simplify to simplest form in order to find something that matches the given answer choice. On the numerical entry, you can enter a non-simplified fraction as long as it fits in the box. Still, it's a good idea to practice simplifying, though, because simplifying along the way may make your calculation easier. So there, it still will be helpful. Practice writing these fractions in lowest terms. Pause the video here, and then we'll talk about these. Okay, here are the answers. The last big fraction topic for this video is how to handle fractions that are greater than 1. If we have a fraction greater than 1, we have a choice about its form. We can write the fraction as either an improper fraction, that is to say, a fraction in which the numerator is larger than the denominator. That's what it means to be an improper fraction. The numerator is larger than the denominator. Or we can write it as a mixed numeral, that is to say, something that is part integer and part fraction. So for example, we could say 5/3 equals 1 2/3. 5/3 is an improper fraction. 1 2/3 is the mixed numeral of the same numerical value, and that's why we can put an equal sign between them. Notice when a mixed numeral is written correctly, the fraction part is always a fraction less than 1. Any part greater than 1 is put into the integer. Also notice that by convention, we write the integer and the fraction parts of a mixed numeral right next to each other, but the understood operation between them is addition. So when we write 4 3/5, what we actually mean, we don't have to write it, but what that actually means is 4 plus 3/5. This makes it easy to change from a mixed numeral to improper fraction form. Write the mixed numeral as addition, and then multiply the integer by c over c, where c is the denominator of the fraction part. So for example, we'll start with 4 3/5. We'll write that as 4 plus 3/5. Now we're going to multiply that 4 by 5 over 5. And of course we're allowed to multiply by 5 over 5 because that equals 1. And that will give us 20 over 5 plus 3 over 5, and those add to 23 over 5. That is the improper fraction form that is equal to the mixed numeral 4 3/5. Sometimes a test problem will give all the answers in either mixed numeral or improper fractions form, so either one could appear on the test. Notice that if you have a choice, improper fractions are almost always more efficient for calculations of all sort than are mixed numerals. Unless the problem forces you to use mixed numerals, you'll be better off changing everything to improper fractions. In summary, we talked about the basic fraction terms and how to think about fraction, the division way of looking at it versus the pi method. We talked about the important idea of equivalent fractions. We talked about how canceling is a form of division. It doesn't mean go away. It means that we're actually performing division. We talked about the importance of learning how to put fractions in lowest terms, also known as simplest form. And we talked a little about the idea of mixed numerals and improper fractions. Conversions between fractions and decimals. Fractions form a group that mathematicians call the rational numbers. Rational because they are ratios. We write a fraction, a rational number, as a decimal. One of two things happens. It either terminates or repeats. Well, those are fancy words. What does that mean? Fractions that form terminating decimals. And of course, terminating simply means coming to an end. So very simply, if we write 1/4 as a decimal, it's 0.25. After 2 places, the decimal just comes to an end. There's no more decimal after that. There are just 2 decimal places. That's it. That's a terminating decimal. Another example, 3/8. That's 0.375. So that's also a terminating decimal. It's a decimal that just comes to an end. That's not an approximation. That's the whole thing right there. So these are terminating decimals. If it doesn't terminate, if it goes on forever, then it repeats. Fractions that form repeating decimals. So for example, with 1/3, that's just 0.333 repeating. So it's the same digit repeating over and over again. Technically, to write it correctly, we'd have to write an infinite number of 3's. That would be inconvenient. Instead, we write it with a bar over the last 3, and that bar just means continue to repeat this decimal forever. Similarly, 1/7. This is not a single digit repeating. This is a set of digits repeating. 142857, 142857, 142857. That whole pattern repeats like mathematical wallpaper forever. And the way we indicate that is by writing the long bar over that entire set of repeating digits. So, once again, fractions, when written as decimals, they either are terminating decimals, decimals that come to an end, or they are repeating decimals, decimals that repeat a particular pattern. There are a few fraction to decimal conversions you should have memorized for efficiency on the test. Many of these are probably already familiar. Basically, you should be familiar with the decimal form of almost every fraction with a single-digit denominator. Now, the really easy ones, 1/2 is 0.5, 1/4 is 0.25, 3/4 is 0.75. You may have these memorized already. If you don't have these memorized, please memorize these. These show up everywhere on the test. These are very important. Another very popular one, 1/3, is 0.3333 repeating. We've met this already. If we multiply this by 2, we get 2/3 is 0.666 repeating, and of course if we round that off, the last 6 becomes a 7. 1/5 is 0.2. Suppose I just multiply both sides by 2, then I would get 2/5 is 0.4. Or I could multiply both sides by 3, I would get 3/5 is 0.6, or multiply by 4, and I get 4/5 is 0.8. Very important to realize that these are just multiples of one another. 1/6 is 1.666 repeating. And of course, if we round that off, we get a final 7. Now, we don't have to worry about 2/6 because 2/6 is 1/3, 3/6 is 1/2, 4/6 is 2/3, but the one that does actually show up as a new decimal, 5/6, is 0.8333 repeating. That's a good one to know. Now 1/7, I'm putting this in a slightly different color, 1/7, I'm going to say you probably don't need to memorize this 6-digit pattern repeating over and over again. If you want to memorize this 6-digit pattern, go ahead, be my guest. That's wonderful. But you don't need to have it memorized. I would say if you just memorize the first 3 digits, 0.143. So that's just rounded off to the 1,000th place. If you know that, that's an excellent approximation for 1/7, and that would tell you virtually everything that you would need to know about 1/7 on the test. 1/8 is 0.125, multiply both sides by 3. We get 3/8 is 0.375. Start out with 1/8, multiply both sides by 5. We get 5/8 is 0.625, multiply by 7. We get 7/8 is 0.875. Notice that I wasn't worried about even numerators, because if I have an even numerator over 8, it would cancel and it would be something else in the lowest term, something that we've already handled. 1/9, that's a bunch of ones repeating. Now this is particularly convenient because it means I could multiply by any digit and it would just be that digit repeating forever. So for example, if I multiply both sides by 7, 7/9 is a bunch of 7s repeating. Any digit repeating is that digit over 9. 1/10 is 0.1. 1/100th is 0.01. 1,000th is 0.001. These should be familiar already. But we can use these to get some other fractions. So for example, 1/20th, well, one way to think about that, I'm just going to multiply numerator and denominator by 5. And the reason I'm doing that is because I want to get 100 in the denominator, 5 over 100, which of course is 0.05. That's one way to think about the decimal form of 1/20th. Another way to think about fractions with denominators that are multiples of 10. So 1/20th, I could write that as 1/2 times 1/10. Well, 1/2, I can write that as a decimal, that's 0.5, and 1/10, of course, is 10 to the negative 1. Well, if I multiply these, multiplying by 10 to the negative 1, as we found 2 videos ago, this slides the decimal place over one place to the left, and I get 0.05. Again, 1/40th, well, this is 0.25 times 10 to the negative 1. Again, slide the decimal place over one place to the left, I get 0.025, and that's the decimal for 1/40th. 1/600th. Well, of course, this is 1/6 times 100th. The 1/6 I know is a decimal, and 100th is 10 to the negative 2. That means slide the decimal place 2 places to the left. And so then this is 0.001666 repeating. That is the decimal form of 1 over 600. With these tips in mind, you should be able to find the decimal equivalent of almost any fraction given on the test. Finally, I will make a few remarks that aren't directly tested, but may help to clear up any misconceptions. All the decimals in this lesson so far either terminated or repeated, but that's not true of all possible decimals. When fractions, aka rational numbers, are written as decimals, they always terminate or repeat. That part is true. The decimals that neither terminate nor repeat are called the irrational numbers, the numbers that can't possibly be written as a ratio. These numbers go on forever in a non-repeating pattern. Familiar examples include pi and square roots of numbers that aren't perfect squares. So for example, here are some famous irrational numbers, of course pi, the square root of 2, the famous mystical number, the golden ratio. All these go on forever and there's no repeating pattern. None of these can be written as a fraction of integer over integer. In this lesson, we studied the common fraction to decimal equivalents and discussed how to generate more using powers of 10. In this video, we'll discuss some of the basic fraction properties. So we're starting out with some very basic properties here. First of all, fractions with a denominator of 1. If we take any integer and put it above 1, then we get something very simple, that it just equals that integer. So 7 over 1 equals 7, or 135 over 1 equals 135. In general, the pattern is n over 1 equals n. Now, it's very important to appreciate that, first of all, we can use this to write an integer as a fraction. So if we had 4, we could write 4 as a fraction. We could write it as 4 over 1. We could write any integer n as the fraction n over 1. Well, why is this important? This is not tested directly. The test is not going to ask you, what does 135 over 1 equal? That's not going to be a question. But this is an important step in problem solving. For example, later on, when we talk about adding fractions, we talk about how to add a fraction to a number, to a whole number. Well, it turns out that it's very useful in that scenario to rewrite the whole number as a fraction. And this is how we'll write any integer as a fraction, just by putting it over 1. So 4 we can write as a fraction, writing it as 4 over 1. That's an important problem-solving step that we'll need later. Second property, fractions involving 0. This is a tricky issue. People sometimes get confused here. So let's be clear. First of all, we cannot divide by 0 ever. It breaks the mathematical law to divide by 0. So in other words, to have a fraction with 0 in the denominator, that actually breaks the mathematical law. That creates something that goes outside the realm where we're able to assign mathematical meaning. So it is, in the most profound sense, something mathematically meaningless. So the test is not going to make you deal with things that are mathematically meaningless. So don't worry. You're not going to be asked to evaluate a fraction with 0 in the denominator. You just have to remember that is an illegal thing. That is something you have to keep an eye out for. If that's a possibility, things no longer make sense. Now, having said all that, it's perfectly allowable to divide 0 by a number. We can have 0 in a numerator. That's perfectly fine. 0 divided by 5 is 0. 0 divided by -3 equals 0. Those are 100% valid equations. We can write the equal sign. That is well within the realm of mathematics there. 0 divided by any non-zero number equals 0. Very important. 0 can never be in the denominator, but is perfectly fine in the numerator. Fractions of the form n over n. So what's going on here? As long as n is not equal to 0, then n over n equals 1. So here n could be an integer, but it could be any other kind of number. It could be positive, it could be negative, it could be a decimal, it could be an ugly radical. It could be any kind of thing. As long as we put anything over itself, as long as it doesn't equal 0, then anything over itself equals 1. The big idea here is we can always multiply any expression by n over n, because multiplying by 1 never changes the value of anything. And this will be hugely important when we get to the point where we have to find common denominators. So this is a really important fundamental idea, and we'll return to this later. Finally, the issue of reciprocals. This is actually a word you need to know. The test could use the word reciprocal in a problem, so you need to recognize this word. The reciprocal of a fraction, a over b, is the flipped over fraction b over a. Again, we're assuming that both a and b are unequal to 0. So for example, the reciprocal of 3/5 is 5/3. The reciprocal of -7/2 is -2/7. The reciprocal of 1/6 is 6 over 1. Well, 6 over 1, as we saw a moment ago, just equals 6. It equals the integer 6. So the reciprocal of 1/6, the fraction 1/6, is the integer 6. So there are a few important properties of reciprocals that it's important to know. First of all, the product of any fraction with its reciprocal equals 1. So they cancel out. So 4/17 times 17 over 4 equals 1. That's a really important idea, and we're going to use this to solve a problem in a few minutes. Second, the reciprocal of any positive integer is simply 1 divided by that integer. So the reciprocal of 6 is 1/6. The reciprocal of 117 is 1 over 117. In general, the pattern is the reciprocal of n is 1 over n. Now, certainly this works when n is an integer, but it turns out n doesn't even have to be an integer. We can extend the pattern, and we can use that same pattern when n is not an integer. So 1 divided by any number, for example, 1 divided by a fraction equals the reciprocal of that fraction. So if I take 1 divided by 3/7, that's going to equal the reciprocal of 3/7, which is 7/3. So that's a really deep idea there. This already suggests the rule for fraction division, which we'll discuss in an upcoming video. So if you really understand this connection well, you will understand fraction division well. Finally, if a number is bigger than 1, then its reciprocal is smaller, between 0 and 1. If a number is between 0 and 1, then its reciprocal is larger than 1. It's very important to have this fundamental number sense, that how big a number is, how big its reciprocal is going to be. Very important to have a keen sense of how big and small numbers are. So here's a practice problem. I'll recommend pause the video here, and then we'll talk about this problem. Okay, the reciprocal of a positive number times the cube of the same number equals 5. What is the number? Well, I'm going to represent this unknown number by x. I'm going to use a little algebra here. So if x is the number, the reciprocal is 1 over x. And of course the cube is x cubed. So we're saying that 1 over x times x cubed equals 5. That's our fundamental equation. Well, that x cubed, literally that means x times x times x. I'm just going to write that out. Now I'm going to take advantage of the first property of reciprocals, namely a number times its reciprocal cancels out. A number times its reciprocal is 1. So 1 over x times x, together that's just going to equal 1. So they cancel, and I'm just left with x times x. So in other words, 5 equals x squared. Now, normally we'd have to consider both the positive and the negative square root, but the problem tells us that we're dealing with a positive number. So because we're given that guarantee, we only have to consider the positive root, and that means that x equals positive square root of 5. In summary, any fraction of the form n over 1 equals n. So in particular, this allows us to write any integer as a fraction, and that turns out to be useful in a variety of circumstances. Fractions with 0, we talked about these. So 0 can be in the numerator, 0 divided by n is 0, but 0 can never be in the denominator of a fraction. That's very important. We talked about the rule n over n equals 1, and again how this will be very important as a multiplier. We can always multiply by n over n, because when we're multiplying by that, we're multiplying by 1. And finally, we talked about the properties of reciprocals.
Often on the GRE, we need a quick way to compare the size of two fractions. Sometimes a QC question will ask us to compare them directly, and other times comparing them will be part of a larger problem. So some of the basic ideas here: if we keep the same denominator, then making the numerator bigger makes the whole fraction bigger. And so if a is a larger number than b, then as long as we're dealing with everything positive here, then a over c is going to be bigger than b over c. So for example, here are fractions that are paired. They have the same denominator. So 4 over 16 has to be less than 6 over 13. 5 over 50, of course, has to be greater than 0 over 50, which is just 0. And 8 over 3 has to be bigger than 14 over, has to be smaller than 14 over 3. And you can think of this just in terms of ordinary things. If there are 8 cookies that are going to be divided by 3 children, well, they're going to get less in the amount of total number of cookies than the case where they have to divide 14 cookies. If there's 14 cookies divided among the same 3 children, then each child is going to get more in terms of cookies. So that's a greater amount. What if we change the denominator and keep the numerator the same? Well, if we make everything positive here, then if we make the denominator bigger, we get a smaller fraction. This is a really big, really important idea. Make the denominator bigger, we get a smaller fraction. So for example, 2/5 is greater than 2/7. When we make the denominator bigger, the fraction gets smaller. 3/11 is less than 3/10, and 7/24 is greater than 7/36. And again, think of it in terms of ordinary sharing. If we have 2 apple pies and we're going to split it among 5 people, well then each person is going to get a lot of pie. But instead, if we take those 2 pies and we split it among 7 people, well then each person is going to get a little less in terms of pie than when there were just 5 people. Again, think of ordinary sharing scenarios that will help you make sense of these rules with fractions. What if we change both the numerator and the denominator? Well, if we change the numerator and the denominator, we can do that in a few different ways. If both the denominator gets bigger and the numerator gets bigger and the denominator gets smaller, then the fraction definitely gets bigger. So for example, we start with 3/8 and we go to 4/7, bigger numerator and smaller denominator. So we started out sharing 3 pies among 8 people, and then instead we were sharing 4 pies among 7 people. Well, definitely everyone's going to get more pie. Another way that we could increase is multiply them both. And of course, if we multiply numerator and denominator by the same number, we get an equivalent fraction, as we've discussed already. So for example, 3/7, if we multiply numerator and denominator by 12, we get 36/84. Those two are 100% mathematically equal. They have exactly the same value. Before we talk about another comparison technique, we have to talk about the very handy technique of cross multiplication. We use cross multiplication when we have an equation of the form fraction equals fraction. Such an equation is called a proportion, and we will discuss these in more depth in the lesson Operations with Proportions. Here we're just going to talk about cross multiplication. If we start with one of these equations, so a over b equals c over d, we can eliminate all fractions simply by multiplying each denominator by the numerator on the other side. So when we cross multiply, we're multiplying these two together and multiplying these two together. And the fact that those two ovals are crossing, that's why it's called cross multiplication. So we wind up with a times d equals b times c. So every numerator stays on its own side, and the numerator from the other side multiplies it. The denominator from the other side multiplies it. Now that we talked about cross multiplication, we can talk about another completely different trick for comparing two fractions, a trick that uses cross multiplication. Suppose in a problem we had to compare the size of 7/11 and 5/8, two relatively close fractions, and decide which one is bigger. I mean, yes, we could use the calculator, write down the decimals, but that would be time consuming, and we'd have to write down a lot of the decimal to see what the difference is. Instead, write the fractions with a double question mark sign between them. This double question mark, it's sort of an unknown for the relationship between them, and it could represent either greater than or less than. So we have 7/11, double question mark, 5/8. And we know there's an inequality between them. Now we get in trouble if we multiply or divide by a negative, but fortunately everything here is positive. So multiplying by positive numbers and even cross multiplying is not going to change that inequality at all. So we just cross multiply. We get 7 times 8 and 5 times 11, so that's 56 on the left and 55 on the right. Well, now we know 56 is bigger than 55. We did nothing to change the direction of the inequality. So, in fact, 7/11 is bigger than 5/8. And we found this with cross multiplication. Here's another example. Pause the video and see if you can figure this out yourself. Okay, again, we're going to cross multiply, which will not change the direction of the inequality. And, of course, 9 times 9 is 81. 20 times 4 is 80. 81 is greater than 80, so that means that 9/20 is greater than 4/9. A final comparison trick is one that involves number sense. And it's about recognizing when a big, ugly fraction is close to a nice fraction. So, for example, suppose we look at this fraction here. Well, that fraction it has to be greater than 80 over 240. But 80 over 240, that's a nice fraction. That's just 1/3. So this fraction, 83 over 240, is slightly larger than 1/3. Well, that's interesting. Suppose we compare it to this fraction, 199 over 601. Well, 199 over 601, that's very close to 200 over 600. But of course, if we make the numerator bigger and the denominator smaller, 200 over 600 is going to be slightly larger. And 200 and 600 also equals 1/3. And so we know that 83 over 240 is greater than 1/3. 199 over 601 is less than 1/3. And so right away, that tells us that the one that's greater than 1/3 has to be greater than the one that is less than 1/3. And so this makes it easy to compare ugly fractions if we can use number sense to see that they're actually very close to a nice, neat fraction. Here's a practice question. Pause the video and then we'll talk about this. The number sense that we're going to use here to compare these fractions is the fact that both of these are relatively close to 3. We know that 3 equals 21 over 7. And 3 also equals 450 over 150. So those are exactly equal to 3. Here, we can express each one of these as the fraction that equals 3 minus something. So, of course, 449 over 150, that equals 450 over 150 minus 1 over 150. And 20 over 7, that equals 21 over 7 minus 1 over 7. And now, just to make it easier, since this fraction and this fraction equal 3, I'm just going to replace them with 3. So it's very easy to see. Well, of course, look at what we're subtracting. Clearly, 1 over 150 is much less than 1 over 7. And so if we're subtracting something bigger, start from the same place, subtract something bigger, we go down more. Subtract something smaller, we go down less. And so the bigger one here has to be the one where we're subtracting the smaller quantity, which is answer choice A. So we talked about a lot in this video. We talked about with the same denominator, bigger numerator means a bigger fraction. With the same numerator, a bigger denominator means a smaller fraction. If you're dividing by more, you get a smaller fraction. And then, of course, you can combine 1 and 2. If you get a bigger numerator and a smaller denominator, then you're definitely going to be bigger, that sort of thing. We talked about equivalent fractions. We talked about cross multiplication as a means of comparison, and then we talked about number sense comparisons.